I'd like to welcome everyone to the webinar series of the Cybersecurity and Information Systems Information Analysis Center, or CSIAC. Today's presentation is entitled Next Generation Cloud-Enabled Architectures. My name is Steve Warzala, and I'm the CSIAC Outreach Manager. Just a few administrative notes before we begin today. First, all phones have been muted except for the presenters. Questions may be asked at any time during the presentation by utilizing the chat function. Time permitting, your questions will be answered at the end of the session. Today's briefing slides will be posted on our website within a few days. Finally, I'd like to take a moment to acknowledge and thank our sponsor, the Defense Technical Information Center, DTIC. The funding that DTIC provides enables CSIAC to conduct these webinars. It's my pleasure to introduce our presenters for today's webinar, Mr. Michael Corley and Mr. Sean Bird from Quanterian Solutions. Mike is a Research and Development Associate who supports work with DTIC, CSIAC, and the Air Force Research Laboratory's Information Directorate here in Rome, New York. Mr. Corley has more than 15 years of professional experience in software architecture design, software development, and systems engineering focusing on applications of computer network and cybersecurity. Mike received his master's degree in computer engineering from Syracuse University, and his recent interest is in the area of next-generation cloud-enabled services. Sean Bird is a software engineer whose work includes system design, systems analysis, software development, and cloud security infrastructure. Mr. Bird is currently supporting work for AFRL and CSIAC. He earned his undergraduate degree in cybersecurity from SUNY Polytechnic Institute and is currently pursuing his graduate degree in computer engineering at SU. We'll now turn the presentation over to Mr. Corley. Good afternoon, Mike. The floor is now yours.
Hi, good afternoon, Steve. Thanks for the introduction. Just provide a little bit of additional context for folks that are listening in. Thanks to everybody for showing up today. And just a little insight, this presentation is really, it's adapted after a lot of the experimentation and the effort that Sean and I and some of our supporters have put in to really solving or finding solutions to some of the harder problems in the efforts of servicing our customers. So really what you'll discover here is it's a mashup of a lot of the seemingly interesting changes to the cloud infrastructures, and really the intent here is just to discuss a little bit of that context and just provide a little bit of insight to where things are ultimately headed. For folks that are, I would say, are really already heavily in tune into where cloud is headed, this might seem a little remedial, but nonetheless, there should be some good information here, and we should all have a good time. So thanks for listening in. Okay, so just basically, we'll step through and cover very briefly the traditional cloud concepts, the deployment types, the public and the private and the hybrid concepts, and the traditional service models, the infrastructure as a service, platform as a service, and the system as a service concepts, and just point out some of the well-known providers. And then we'll follow that with a little discussion on virtualization, which is kind of the heart behind the infrastructure as a service component. In fact, the discussion is largely focused on the infrastructure as a service portion of this. We'll talk a little bit about virtualization and just a little very brief review of the hypervisors, and then talk about some things that are interesting, in particular unikernels and containers and the whole microservices concept. And then following that, Sean will get into some of the details of some of the latest and greatest of the tools out there and the great influx of everything that folks are trying to put into place as the cloud's kind of rapidly evolving. So basically, what is cloud? You know, it's something that's been around for a long time. It's the adaptation of the service-oriented concepts. It's abstraction at its best, and what you're ultimately doing is exposing computing resources through well-defined service layers is really what you're doing. And in that concept, along those lines, the traditional cloud deployment models have been in place for some time are the public cloud concept, which is really the idea, the notion of third-party providers making computing resources available to the public or multiple organizations. And there's certainly some constraints associated with that. They're multi-tenant, and some of the challenges that most folks are concerned about is a limited control. Where does my data go? What guarantees are there associated with my data? You can't access hardware and often can't affect performance or storage outside of the service agreements that are in place. And it's also difficult to achieve some of the compliance requirements that are out there, having to do with financial information that's maintained, the Sarbanes-Oxley or the public card, or some of the PCI type things, the payment card industry kinds of compliance requirements. So moving right along, following that is the notion of the private cloud, computing resources that are available to a single organization or governed by that organization. And they're advantageous because they're you're dedicated hardware and you have that control that you don't have otherwise over where your data resides and performance and access and things of that nature. And of course, it's easier to achieve compliance. And it really determines the needs of the organization determine whether you go with a public or a private model or even a hybrid model, which is a mixture of them both with the right orchestration in between. And certainly the goals. For the consumer, the goals are always scalability, cost effectiveness. You're looking to save money and to do a better job at your business process model. And from the provider's perspective, it's always about making money. So just a very brief review. In terms of the providers that are out there are many, many, many providers, and I've just listed. It seems like Amazon gets a lot of the press these days. So they all get a lot of press, and our line of work gets the Amazon cloud that we bump into, and also the Rackspace, the OpenStack environment, the leading open source cloud provider. We've done an awful lot with that here in our experimentation, so we list that as well. But there are many, many providers. So just to briefly cover the cloud service models, because this will kind of frame the rest of the discussion. There is the kind of the traditional three-tiered model, the infrastructure as a service, which is really an abstraction or a management service layer over the physical infrastructure. So virtual machines, or the complexity of the complexion rather of the virtual machines, Windows machines, Linux machines, whatever else out there, those are all made available to the consumer through a service interface or ultimately a dashboard. And following that is the abstraction of the execution environment itself, which typically entails, a tailored operating system, the development tools, the things that are needed by the consumer, and then lastly, the system as a service concept, where the consumer essentially says, I don't care about anything except I need to have access to the applications that I need, whether it be development portal that's accessible on demand or your email, whatever it is. But your concern is dealing holistically or solely with the application itself and no concern for how that's provisioned. So following that, if you keep those things in mind, I'm sure most folks have heard those terms. If you haven't, you can look into them a little bit further. But the idea here is we're going to talk a little bit about how some of the newer technologies have an impact on the infrastructure as a service model. Okay, so as we're kind of alluding to, infrastructure as a service is kind of the heart of virtualization is the heart of IaaS. And it's traditionally accomplished with virtual machines. And there's a number of different flavors of virtualization that I'll just touch on here for a moment. There's full virtualization, where you're essentially implementing, simulating the hardware to allow guest operating systems to run unmodified. They don't know that they're running on a virtualized environment. There's para-virtualization, which in order to improve performance, there's subtle modifications that are made to the guests in order to allow them to do a little better job. And in that case, of course, they're certainly aware that they're not running on the bare hardware because of that case that they need to be modified. There's the hardware-assisted virtualization, which you often see in your BIOS settings with your PC. There's some of the support that you can turn on to allow them to do a better job, hardware assisted. And of course, there's the key piece here that's central to it all, the hypervisor. And there's traditionally two types of hypervisor, a type 1 or a bare metal, which allows your guests, your virtual machines or what have you, to run directly on the hardware. Some well-known are the Zen Server, which we work with, Microsoft's Hyper-V, VMware, which most folks have heard about, and ESX Server is a well-known type 1 hypervisor. And then, of course, the hosted, which are hypervisors that run on top of a host operating system, such as VMware Workstation or VMware Player or VirtualBox. Those are the two flavors, the traditional flavors of hypervisors. OpenStack itself is the leading, well, it's been the leading open source cloud solution. It's founded by Rackspace and NASA, and it's essentially a collection of interrelated projects that control pools of processing resources. Nova is, for instance, the management process for the IaaS hypervisor component, and the others, Glance and Swift and some of those. Neuron provides all of your networking management. Cinder provides some of the block storage component piece parts, and these are all, you can look these up if you're not familiar with them and you're interested. Keystone provides an identity management component, and Glance provides some of the image management components and how some of that's handled. But again, I don't want to get into too much detail. It's something that you're either interested in or you're not, and it's interesting open source cloud solution that's supported by more than 400 or 500 companies at this point, and you can look into that further if you're interested. So to kind of drive this forward and start to get into some of the more interesting aspects, let's just cover briefly the idea behind how the hypervisors are utilized within OpenStack and some of the other cloud solutions. libVirt turns out to be kind of essentially an API or a daemon, a management component that allows the solution to use or to essentially remain hypervisor agnostic. It's a management API layer that allows any type of a hypervisor to be used that conforms to the API into the interface. And you can see that concept on the right-hand side of the diagram, that through the libVirt API, KVM or Zen or QEMU or even LXC, and that's how originally some of what we'll talk about in a little bit, the container technologies, which I haven't mentioned yet, but I will, are incorporated. I think there's a diagram later on that illustrates that from an architectural perspective, how some of the newer technologies, the container technologies, can be phased in. So as we move on here, some of that will get more interesting and more clear, hopefully. Okay, so having said all that, there's a lot happening in the cloud. There's lots of new tools, particularly later on, Sean's going to get into how this concept of orchestration is done, but it kind of narrows down to two real fundamental concepts. Operating system level virtualization, this notion of process isolation that's achieved with containers, and this idea of microservices. Containers, which I'm going to talk about a little bit more, can be thought of very much like virtual machines in terms of how they look, but they're not. They actually share the host operating system. Microservices are something altogether a little bit different. They're specialized single-purpose operating systems that only carry the dependencies necessary to carry an application, to run an application. They're very small and they're very transient. And they don't exist for a long time. A unikernel or microkernel instance will pop up, satisfy its purpose, and then it will go away. And what becomes very interesting is once systems are deployed with these technologies in place, the challenge becomes how do you administer, how do you manage, or how do you control and make the guarantees that you normally would, and that all centers under the area of orchestration, where a lot of effort is being placed right now on how the orchestration is to be done and what real changes or impacts these have on the whole DevOps concept. Is it does make some very significant changes to the way that that's done currently, and particularly how IT professionals would deploy network services and how these services are developed as well, and how they're administered and deployed. So let's see. We continue on here. So as we started to allude to, the container concept first before we get into unikernels. They're conceptually similar to a virtual machine, but rather than a full guest operating system with a hypervisor in the middle, what you don't have any of that. Essentially what you have is the Linux kernel, in this case the Linux kernel being shared, and these containers use the native system call interface. So the isolation, the process isolation, is achieved through some of the newer Linux kernel features, in particular the control groups and the kernel namespaces. So I've got a slide in the next, or a diagram in the next slide that'll show that. But the chief advantage of these is because there's not the need for a guest operating system nor a hypervisor, you can have lots of these Docker containers, applications running inside these containers. I said Docker containers. I'm kind of alluding to the next step here. But lots of applications can run in instances of these containers on singular hosts. They're much more efficient and they're much more flexible, and that leads to cost effectiveness. And a lot of folks are beginning to have been investing in these for some time. But again, the part of the issue or the challenge that arises is how do you control and how do you secure these things? How does it break existing concepts, existing policy? If you're going to implement policy or follow conventional practices for control and security, how does it change those things, and what do we do about it? And there's a lot going into that right now in terms of how that all reconciles itself. So let's see. So here's the diagram that kind of illustrates it. So what you see over on the left-hand side of it is you see the typical arrangement. In this case, a hosted Type 2 hypervisor that's sitting on top of a host operating system with several guest host operating systems, and then the applications themselves that would be served up or run under those guest host operating systems. And on the right-hand side, you see, again, the server and the host OS, but all you see now is an instance of a Docker engine. I haven't talked about Docker yet, but Docker's kind of the leading technology provider around containers. It provides an ecosystem, a full ecosystem around container technology. So the idea is, on top of a host OS with the Docker management daemon running, you can have all these little applications that run in isolation on the host, but without the guest OS and the hypervisor, which you see on the left-hand side, making a lot more efficiency and a lot more flexibility to run. We'll see. I'm going to talk a little bit in the next slide how applications are managed and how they're deployed in a much more simple context. So as I started to allude to, Docker is the leading, it's a service-oriented container ecosystem for Linux. And the way that these are provisioned or made available is through this notion of images. So basically, to try to capture this, applications run in containers, but they're built from images. And these images are made available in a Git-like type repository. If you go to the Docker Hub, you can see lots of official, public or private images of application stacks that folks have deployed. So if you're a network security professional, for instance, and let's say you use Wireshark and you use Snort and you use TCP dump and some others, you'll find that you can do some basic searching and you can find an image that already contains all those piece parts. And generally the way it works is something along the lines of what you see in the picture off to the right. You start off with a base image, which might be an Ubuntu rev of some sort that's stripped down. And as you begin to introduce applications, you introduce these applications in terms of modification layers or image layers. So that means that this image stack, when something changes, when you originally pull down your application, you're going to pull down the base image with all of the dependent applications in their respective image layers. But then, as changes are made, the only thing that comes down is the modification layer where the change was made. So if you add a new application or you swap out a version of one of the tools in a respective image layer, only that is what's coming down at that point. And that's all made available through the Docker daemon, which is a system as a service daemon that provides the management layer around all this. So it greatly simplifies the application deployment and distribution problem, because you're not moving all the dependent information around. You're moving around only that information that needs to be moved around upon, addition or modification. So it's an interesting model for that reason. The Docker Cloud is something that's relatively new. You can look into it, and rather than infrastructure as a service based around virtual machines, they've got a full service concept that allows the deployment of application in containers on demand. So again, one of the many instances of some of the neat things that are going on that you can look into. Okay, so having said a lot of what we said earlier, we had the slide on libVirt and OpenStack, and what this shows is through a RESTful model here. You can see that the glance was the OpenStack project that does image management, and you can see how that's working with the Docker registry here. And through a RESTful HTTP API and using libVirt, you can get Nova to use or take advantage of containers relatively seamlessly within an existing OpenStack deployment model. You can start to phase in some of these technology piece parts yourself. Now, this is an older slide. There's lots and lots of ways that folks are doing things, but this is a very legitimate way to look to achieve your own cloud deployment model that incorporates containers today. And in fact, this is here because this is one of the first things we did in our experimentation, to start to understand some of these and to look to provide some of the latest and greatest solutions to our customers. We take opportunities where we can in our requirements to phase some of these things in with our customers' consent to try to understand and learn and keep them cutting edge as well. So. Okay, so having said all that, that's the container concept. The unikernel concept is something that's even more interesting. And really what they are, I'm not going to speak too much about the specific instances, but you can see if you go to unikernel.org, over the picture off to the right underneath it, it's in red, you get quite a bit of information there. And I would recommend checking that out if there's any interest, because these are things that are absolutely moving out in the wild, and we will run into them and we will have to deal with them. But essentially what they are, I mentioned earlier, they're specialized, single address space, single purpose machine images that are constructed using library operating systems. So basically put, you're compiling high-level language code directly into machine images, and essentially the operating system structures or the piece parts necessary only to run a specific application. There's no general purpose OS. It's just that specialized code needed to run an instance of an app. And the advantage or the result that is gained from that is certainly reduced code size and reduced resource footprint. They're very small, so they're very quick to boot. You can boot thousands of them. They don't exist for very long, other than to serve their request and they go away. They're performance optimal because they only carry what they need, and they shrink the attack surface. You don't have things that are around that you're not using to exploit, like shells and other processes that would normally, be available in a conventional operating environment. They're exploitable. They're not just there. They're just not there. And they run, like we mentioned, they run directly on a hypervisor or on a container or in bare metal hardware, and And we're just really beginning to experiment with these. We don't know an awful lot about the details, but some of the popular ones traditionally have been the Rump Run, Clive, and Mirage OS, and Include OS is a neat one as well. They're all neat, and I'd recommend checking into them a little further if there's any interest there. Security, there's always the question of security. They're transient, and these instances of applications, they come and go, and that's a good thing and a bad thing. The bad thing is, from the administrator's perspective, is how do you manage these things? How do you institute the level of guarantees and control? And folks are working that issue. And certainly the advantage we mentioned out, the immediate advantage is that reduced attack surface. You don't have lots of code that's available for exploit. But in some cases, and there's a little reference there where you can look at a Linux journal article that we came across, is because of the way these are provisioned, not in all cases, but in some cases, you don't have the typical user kernel boundary as you had with the traditional OS. Like if you're familiar with the ring model concept, where upon gaining root access, you go through a system control, access control thing, and there's hardware in the middle that forces you to go through the system call process, that uniform access to entering into privilege mode. That doesn't necessarily exist. And as a result, what some folks are doing is they're looking to use hypervisors for that multi-tenancy, or to pick up that feature where it's a necessity. But again, we're not overly spun up on these, and they're very interesting, and they're things that folks are absolutely investing in. So I think the more aware we all are of these, the better we can do as a community. Okay, so yeah, this is just a little bit more. I think I mentioned it, the risk and the challenge. They're transient. The unikernel instances of applications in unikernel instances are only long enough to service a request. So from an administrative perspective, how do you implement policy? So if something bad is discovered and the commander or the boss says, execute policy A, which means patch the web server, traditionally you would patch the web server, but in the instance of this deployment with unikernels, the web server will only exist long enough to service a request, and it would be gone. So the changes are such that the way that things are currently done are not the way they're currently done now. Clearly, they're lots of folks are making some suggestions and absolutely implementing some prototype concepts for how this would be achieved. But I think it's one of the areas that's really up in flux right now, and we're not for certain how this is going to work itself out. But where it centers in is in the area of orchestration. There's lots of approaches being provisioned for how you manage these piece parts. As Sean's going to point out here in some of the review of the tools that are coming up next, it turns out that as you have lots of virtual machines behind service layers and containers, lots of containers running across clusters of virtual machines and applications that are deployed in as unikernel instances deployed in containers, you lose visibility across the boundaries. So the whole orchestration and management becomes a hard thing to do. And that's where a lot of the attention is being directed to. So, having said that, I'm going to turn that over to Sean now, and he's going to kind of give you an overview of some of the essentially the cloud toolbox, some of the tools that are out there in the wild, and the way folks are looking to address some of the issues that we discussed a little earlier. So here you are, Sean.
Thank you, Mike. So just to go over some of the tools that are out there right now in terms of orchestration and management and configuration of all these different disparate piece parts of this cloud stack. This is just a long list of some tools that I had thrown together, just of the ones that I had come across with in our experimentation over here at the CSIAC. And this is not all of the tools available. This is just a small subset. It really is kind of the wild, wild west of tools. There seems to be a new startup company every 5 minutes with one of these tools. We're kind of hoping to be bought out or picked up for support by one of the larger companies like Microsoft or Docker, or supported by such to get rolled into that open standard. And some of them have kind of achieved that, and some of them are homegrown tools based on infrastructure that a company needed. Like Kubernetes is the main container orchestration tool for Google and Google's Gmail and Google Drive, and that's largely what their infrastructure runs on for their containerized applications. And so they grew that themselves for a need that they had, and the same thing goes with like Apache Mesosphere and other tools within this list. So all of those, I can't hit the buttons here. Sorry about that. So all the tools fit within this kind of 7-layer stack of the cloud ecosystem, and you can see some of the tools that were on the previous page are in here, and it starts all the way down, kind of like what Mike was saying, with your physical infrastructure, your servers, your actual physical devices, your virtual infrastructure like your hypervisors and your VMware vSpheres and your Hyper-Vs, your base operating systems, which will be your virtual machines, and this can kind of be that layer 3 can kind of be taken out if you want it to. You can sit containers right on bare metal hypervisors. For our experimentation, we put them within virtual machines and then containerized on top of that. You have your different container engines. A lot of people think Docker is the only name of the game out there, and really it's not. There's Rocket from CoreOS and OSV. Those are the kind of the 3 biggest right now. There are also some others that are messing around in the field. Then you have on top of that your scheduling, orchestration, and workflow layers, and these kind of all mesh together and kind of work with each other to create a highly flexible and configurable environment that is easy to manage from a admin perspective. On here. And again, about the container engines, Docker, obviously from the company Docker in itself, is the most widely used and accepted mostly as the standard for containers. You have Rocket from CoreOS, which is aimed to be a quote-unquote more secure container solution with signed images and user and root separation. They do a little bit more fixing up under the hood to give you some guarantees for security. Since I have created these slides, Docker has done some steps to catch up to Rocket in those areas. I still think that Rocket might be a little bit more ahead of the game in terms of being security-minded, while Docker is more focused on providing as much automation as they can for tools to incorporate into their infrastructure. And then you have LXD from Canonical, which has a REST API access and is more of a VM-like container, and not really a lightweight container. And it obviously sits on top of Ubuntu and is their main tool. So orchestration, like it says, the main goal is to provide automated container management as well as guarantees for multi-container services in Container Engine. So you have all these different containers, thousands of containers running services, and you want to have guarantees that these services for quality of service and security and just infrastructure guarantees that when these containers go down or something goes wrong, I'm going to have these systems that can be actually repaired, and not just these million of piece part things that you have to kind of collect after they fall. So Marathon and Apache Mesosphere and DCOS, they're kind of treated as one machine. They're multiple physical node scaling. So you have all these large data centers that have huge machines with many CPUs and RAM and hard drives that they have to scale across. And how do you do that in the right way? I mentioned Kubernetes before, which is used by Google. Think of this as when you spawn up a Google Doc within your Google Drive, that is actually a containerized process that is going off of a shared network drive. And that is load balanced using Kubernetes. There's a proxy service that sits in between and distributes your request and spawns your container on the appropriate hardware that has enough resources available. Swarm from Docker, as well as the data control plane, which is brand new. I should have incorporated that into here as well. That has just come out from Docker, and that's their Kubernetes orchestration type of tool for larger infrastructure. It uses the Docker Swarm, which is the native Docker clustering tool that uses native Docker API, and it's what a lot of tools integrate with for third-party integration. For our experimentation over at Quanterion in CSIAC, we used Rancher and Rancher OS to do our host and cluster management, as well as some service management for some experimentation that we were doing with Elasticsearch and the Elk stack, which is Elasticsearch, Logstash, and Kibana. So I'm just going to go over in the next couple of slides here what Rancher is and how that kind of played into our experimentation a little bit. So Rancher can hook up to its own Rancher Cattle container management service, which is another service other than Docker Swarm or Kubernetes or Apache Mesos, but it can integrate with any of those tools and try to be that one solution fits all for your container orchestration. So whichever tool you have underneath it as your container engine, Rancher aims to integrate with all of them with one API. Security management, it incorporates some access control with various tools, whichever one that you would have in your organization, to allow certain people access to different containers and services, as well as the management and creation of those services. If you have testing that needs to be done on the development side or a DevOps side, and you need a larger amount of machines, you don't want a team to hog up all of your resources, so those type of restrictions are incorporated into that. And this is just a diagram of kind of how the container engines sit on top of Rancher. And as you see, there's Swarm, the native Rancher orchestration, which is Rancher Cattle, and Kubernetes. And the API for Rancher just sits right on top of all of those three. So it's kind of agnostic to those different tools. So some security risks that is associated with these containers are inherited risks with CA-true. Containers, I think Mike went over earlier, are just CA-true or BSD jails, and there are some security risks that are kind of inherited with those. Secondary CH roots back into the main file system that could allow containers access to areas of the host system they shouldn't be, or even other containers. Privilege escalations, which would be like breaking out of that jail and running your container as root and allowing root processes to be spawned off of your containerized process. Local network access, obviously you wouldn't want someone to break out and be able to access your local network. And arbitrary code execution, which would be executing code that would be inserted into the container and then broken out and executed on the host to cause all sorts of havoc. So Linux capabilities, allowing granular specification of user capabilities with Linux kernel services. So there's a lot of kernel services that are leveraged by Docker and the other tools in order to make these containers as secure as possible. And it's really under construction, and people are breaking these tools. It seems every other day there's a new security flaw that they're patching that needs to be worked around. Also, Docker uses Linux namespaces and C groups to mandate resource constraints. So C groups limits its resource consumptions for each container and manages that it uses these to manage that across all of the containers on a system. And it creates namespaces for each container, which isolates them from running, isolates processes from others. Container image validation, this actually is not true, and I should have taken this out of here. Since the creation of these slides, Docker has implemented container validation with their Docker Cloud. Before, it was kind of the Wild West of containers for the Docker public registry. So anyone can upload a container base image and call it Ubuntu 14.04, and people would think that that was legitimate, and it could actually have arbitrary code execution or any of the security vulnerabilities that we had talked about before. So now we're just going to go over some of the experimentation that QSI and CSIAC did with these tools, including Rancher and the what is now known as the Elastic Stack, or the ELK Stack, as it's more commonly referred to. So Rancher and Rancher OS, I kind of talked earlier about how containers can be spawned on bare metal hypervisors. So on the left, you have Rancher, which is we have Xen Hypervisor, a virtual machine, your Docker engine, and then the Rancher manager is actually a container and managing the containers alongside of it and on other systems. Whereas on Rancher OS, you have your Linux system kernel, your Docker, your system Docker engine, and then a user Docker engine. So they're using a Docker engine to run system services on the host, as well as a separate Docker engine to run your Rancher manager and other service level containers that you may be running. So for Elasticsearch, this slide and the next slide are just kind of a capture of what we were trying to implement with Elasticsearch over a couple of machines that we had here at QSI. And we had two physical machines, both running Xen Hypervisor, and then Linux virtual machines within those hosting Docker engines. Within the Docker engine environment, we had Rancher managers on each machine, orchestrating Elasticsearch nodes that were all clustered together to create one Elasticsearch service. And then incorporated in that externally, we had Logstash instances and Kibana instances interacting with this Elasticsearch cluster that you see in the middle here. This slide more kind of illustrates the overlay network that is incorporated with Rancher, and there's a particularly interesting part of Rancher, I think. So in order to accommodate containers that would be within the same service and would need to interact with each other on a local network, how do you accomplish that and orchestrate that across multiple geographic sites as well as multiple machines? So to do that, Rancher implements an overlay network and these TUNTAP devices within these containers to create a private network just for these containers to interact with each other across multiple sites and hardware resources. And this kind of illustrates that across the different Linux VMs as well as hardware that's on the bottom. This may be hard for some people to see, but this is just an example of the Rancher main page for the infrastructure that we had. And we had a few of these machines inactive, as well as the two in the middle being the active ones that we were actually running the Elasticsearch containers on. And you can see like the red dots were some inactive nodes that we were playing with, but it really captures the ease of use for this, that you can just see all of the containers within your service and where they are on your actual infrastructure. And you can see next to each container name, like those red dots in the middle being containers, a IP that is a 1042.116.72, for instance, on Rancher 1. That's part of the Rancher overlay network. And you'll see that all of the containers are on the 10.42 subnet, being able to talk to each other. So this is the application or stacks associated with Rancher. So you can create clusters of containers or singular containers and string them together to create a service that you want to provide. And this will give you health statistics as well as drill down capabilities into the CPU and RAM load of these different clusters and containers within these clusters. So right here, we were playing around with some of the Elasticsearch cluster capabilities and cloning them. It makes it very easy to clone. For instance, there's Elasticsearch cluster old, which is just a 20 container service that I was able to clone pretty much instantaneously and name it something else, and it will spawn 20 new containers, all hooking up automatically to my network shared drive and being able to cluster together and create a service on my Elastic Master Prime, which is also within that Elasticsearch cluster. And then, of course, as any engineer would, we just tried to break whatever we found and do some fun stuff. So we thought, well, if I want to run a Windows application or just any application I want, how do I run whatever I want within a Docker container? So we started playing around with some, and this is not entirely recommended. We started playing around with some base images and using QEMU to emulate a Windows 7 virtual machine within a container. So you get some pretty intense layers of inception and abstraction inside of this. And it was a little bit complicated to do, but we ended up actually doing it. And it was a little bit slow. And this is just kind of a illustration here for the network setup that had to be involved. So you have your physical NIC, which is in that purple in the hypervisor layer there. You have your virtual machine, which is a virtualized NIC that is bound to it. You have your TUNTAP bridge, which is what all containers sit on. They all sit on a TUNTAP bridge. And then within your container, you have a TUNTAP bridge, and then a Windows machine, which is going to be bound to that. So it got a little bit confusing, but we were able to pull it off, and it was a working Windows machine. It wasn't working extremely well, mind you, but it was working. And that's just, you know, some of the fun things we were trying to do. This is just another slide illustrating some of that. And this is a diagram illustrating the layers that we had in place there. So you had your base image for your container and your QEMU, which is also a layer within your container. And you can swap out these layers to update the tools that are within these application stacks. You cannot, however, containerize the Windows image that you put into there. So that was something that was fun to discover. And this is just another illustration. We implemented this across a bunch of virtual machines and kind of tried to cluster them all together so they can interact with each other. And I believe that's all we have. If there are any questions.
Hey, well, thanks, Mike and Sean. That was pretty interesting stuff you're working on there. So I do have one question I'd like to run by you. So how are containerized apps in Linux? Are they cross-platform with Windows? How does that work going across the different systems like that?
So currently, in our not to our benefit, we didn't have Windows container services within our presentation because they're brand new and we're not as familiar with those yet. But you can containerize Windows apps within Docker for Windows, which I'm not quite sure how they're doing under the hood, doing isolation and stuff. But you can do that with, I think, Windows 10 and Windows Server 2012 and above, I believe. But Linux, obviously, a Linux app cannot run within a Windows environment. So in order to quote unquote run a Linux app in a Windows environment, they need to do optimized OS virtualization of a Linux operating system within the Windows environment and then running the apps on top of that. Now, it is not the case that this goes the other way in that a Windows app can run in a Linux containerized environment, because there is no, unless you kind of do what we were trying to do with a Windows virtualization in QEMU, which is not efficient at all, you do not have the dependencies that Windows apps would need within a Linux environment, since containers share the kernel and operating system with their host.
Mm-hmm.
Okay, thanks
I go further to say with that, Steve, that as well as if you look into Windows adoption of the Linux platform here, the things that are available with the Bash and all that, we're going to see more and more of those complexities ironed out here. It's going to be interesting to watch how that all happens.
Okay, we'll look forward to seeing how that plays out. So we do have another question here. Folks are wondering if you've investigated the performance differences in running HLA federates within containers versus guest VMs. Have you looked at that question before?
Well, it's a specific kind of thing you'd carry out, and at this point, what we've done is, aside from the resources that are available from specific studies folks have done online, we haven't. It's just the fact that you don't have that guest operating system nor hypervisor layer, so naturally you'd expect them to be much, much more efficient. And there are lots of folks out there that have. Unfortunately, we don't have any references to some of those in this presentation slide set. I suppose we could augment the slide set and put some of those up there, but they're relatively easy to find out there. But we haven't specifically looked at some of the instances of some of the performance enhancements that you can gain.
And on top of that, we haven't done so much in terms of thinking about how this would integrate into current DoD or military systems that are in place now. We wanted to get a good understanding of the fundamentals that sit behind the technology and how this is going to move forward. And a lot of this is within the infancy of itself. So these tools aren't mature. They're just becoming mature enough to where people within the private industry are running their services on top of them. And so it's something that the government needs to be aware of, and especially cybersecurity professionals need to be aware of for all the security vulnerabilities that may exist that aren't discovered yet within the field. And so that was pretty much what we were aiming to do.
Yeah, it looks like you're kind of right on the cutting edge with these new technologies that are coming out. So, it looks like
one of the things part of what we ran into, Steve, that's interesting is as we were evolving with these and learning and keeping up is the documentation for how you get some of these things to work and configured would change almost daily, particularly the Docker side components. We watch that change pretty frequently over the period of just a month.
So the Docker, the Docker is in development. So you're kind of doing this. They're doing it in real time, and you're kind of watching it happen in front of your eyes as you're trying to use the technology as well.
You got it. Yeah.
Do we have any other questions from the audience for Mike and Sean while we have them on the line? Anything else you gentlemen would care to add? We don't seem to have many other questions rolling in right now, but if there's any final thoughts, if future directions where you might take this investigation in the future, have you got plans for the future for this?
Some of the areas that we had looked at implementing this sort of technology is in the area of testing and simulation and how that really works in a research aspect for testing and development. So how can you create these highly flexible simulated networks and application environments to really test things in, and what is the fidelity that you can achieve with that, given how much hardware that you have?
Yeah, that's Steve. Sean makes a good point there. That's one of the things that kind of got us in this path. One of the difficulties that our customers have had is, testing and deployment and data capture and having access to high fidelity test environments, and we set off on an endeavor to try to, the fact that some of the computing power is where it's at today with big servers and lots of memory, could we take some of these technologies and put them together and start to simulate enough of the network with the fidelity such that we could start to enable some of these things that were otherwise not cost effective or bound by folks needing to travel around and getting access to specific infrastructure. And we've answered some of those questions, but it's that. And we also are really interested in how the software-defined networking concepts would feed into this notion of devices that how the whole idea of separation from the smarts within the network, the movement of data is pulled out into a control layer, and the internal pieces that move information around become, not so smart. So the actual movement of information, it's pulled out to the edge of the network into a service layer, and you get that separation, that fine-grained separation of control and data. How those devices and how those methodologies are going to phase into the cloud environments and ultimately upend the way that some of the data centers are provisioned and laid out. How's all that going to work? It's a lot. So.
Oh, that sounds that sounds pretty interesting, and we'll look forward to seeing how it develops, and what new capabilities it may enable, and
Yeah.
additional capability to provide down the road. So
yeah, it's a lot of stuff to sift through. So this is our first attempt at sifting through it. So we're interested in feedback or interested in anything that folks have observed out there that might get us all a little bit smarter in the domain.
All right. Well, that sounds great. I want to thank you guys for taking the time to spend with us today and share the information on the work that you've done. It's quite interesting. Like I said, right here on the cutting edge, kind of bleeding edge, really, and real time watching things change before your eyes. So once again, thanks. It was a great presentation, and thank you, and thanks to the audience for joining us, and we'll look forward to seeing you next month.
Okay. Thanks, everybody.
Thank you.
Bye-bye.
Bye-bye.